All right, let's keep going. On our build up to quantum mechanics to what we currently use as a working model for the atom. So years keep going by since we left off. The technology got better, and they realized that the lines on an atom's atomic spectrum were actually groups of closely spaced lines, and this to them pointed out that there must be sublevels. Okay? Which was a bit of a surprise. It means it can't just be nucleus and then very discrete levels. There's got to be other levels within the levels. And then we keep going back to this light being a particle and a wave. So more and more, it was wave theory was starting to win out, and both matter and light were showing properties of being a particle and a wave. And this is a really famous experiment done by a scientist named Compton. He shot X-rays at an electron, and in a collision between two particles, it says right here, momentum is always going to be conserved in any collision, and that's something that we cover in grade 12 physics. The momentum before the collision total momentum must be equal to the total momentum after the collision. So this X-ray came in and hit this electron, and the electron goes flying off, and the energy gets transferred from the X-ray to the electron, and then not all of the energy gets transferred. So some gets transferred, that's why the electron flies off, and then this light energy and now continues on. Yes, continues on its own. And what he found was the momentum of this X-ray plus the momentum of this X-ray did equal the momentum of this photon plus the momentum of this photon. But what would happen for momentum to be conserved? This thing is lost energy from here to here. What's going to change about this photon? And its color changed, or you might say that its frequency changed from before the collision to after the collision. And when you actually do the math and you look at the energy of the photon before and after, momentum is still conserved. And this is a massive experiment because light here in this experiment is acting as a wave and a particle at the exact same time, because particles obey this momentum as being conserved, and it was, and it's acting like a wave because its energy and its frequency, and it was a really mind-blowing experiment for them. Then this Frenchman named de Broglie came along, and he said, hey, light seems to be acting like a wave and a particle. Can matter act like a wave and a particle too? And he was right. Okay. When you fire waves at a slit, you get what's called a diffraction pattern. And when you fire electrons at a slit, you get the same pattern. You get this diffraction pattern, which is really, really bizarre to them. And if you want to see a video of it in action, you can go to YouTube and search for Dr. Quantum double slit experiment. There's the link. You can't copy it though, but there it is there, and you can watch it, and it's explained quite nicely there. Now, why do electrons exhibit this behavior? Right. So here's my slit. Now, if a wave is coming at this, yes, when it hits this slit, it starts again and heads out in all directions. Yes, and it turns out that let me just go up here, that electrons do the exact same thing. When they are fired at these slits, they come in like this, and some go this way, and some go this way, and some go this way. They diffract through this opening. Now, electrons do it because they're incredibly small. If I was to pick you up and throw you out a door, the door would be the slit, you would be the particle as I throw you out the door, you're going to go straight through. Now, there is a probability that you might actually diffract and go kind of around the corner, but that doesn't it's not seen in our lives because we're all too big. To get the wave property of matter, you need to be really, really small. And then finally, another big one is Heisenberg, and he came up with the uncertainty principle. He's German, 1927. Electrons are super small. Okay? And now physically, if I want to look at something, what has to happen? So here's me, and here is the thing that I'm looking at. What has to happen? Yes, there's the sun. Light has to come down, hit this thing, and then go to my eye. Yes? So physically, what has to happen? Light bounces off object, then to eyes. Yes? But light is energy. True? So if light is energy, if this was an electron, energy hits the electron, so when and then comes to my eye, what's going to happen to the electron? Okay? So when light hits an electron, it is given energy, yes? And then what's going to happen to the electron? It's going to fly off. Fly off who knows where? Yes? No idea. Boom, gone, because it's so tiny. Yes? And so therefore we can never truly know where it is in physics, quantum mechanics. We say we never completely know its position, the position of electron, or how fast it is moving, velocity. Yes? You can't know these things with absolute certainty because it's so small, because as soon as you try to observe it, so if you try to look at it, it gains energy and is gone. Okay? Oops. You just can't. The act of observing affects the system too much. So Bohr's idea that atoms are in fixed orbitals, that means that's crap. You can't know exactly where they are. They're not going to be exactly where we think they are. And therefore, scientists started to move to where there's a high probability of where the electrons may be found. We stop now talking about, no, that's where it is, and instead we talk about, we're pretty sure it's over there somewhere. And now we are ready to fully discuss what quantum mechanics is, and we'll do that in the next video.